Today's video will cover partial derivatives. So the idea is we're looking at a function of two variables or maybe more than that. How do we find a derivative? Before we jump into that, we're going to do a quick review from calculus. And the question is, what is the meaning of a derivative? So we know how to find a derivative, but what does it actually tell us? And if you remember, there's a few main meanings of a derivative. One, a derivative will give us the slope of the tangent line. A derivative also will help us calculate instantaneous rate of change. So now what we're going to be looking at is some function f of xy, so that's a function of two independent variables, x and y. And the idea today is what happens to x if we hold y constant. So if we hold y constant, how is x changing? Or what happens if we hold x constant? What does that do to y? How is y changing? So that's going to lead us to the idea of a partial derivative. So in this first objective, you can see a little bit of a sneak preview at our notation. So you'll see that little x and little y, that tells us our partial derivative. So partial derivative with respect to x, partial derivative with respect to y. So like before, let's start with our definition. Let's say that z is some function in terms of x and y. The first partial derivatives with respect to x and y are those functions. And here's how it's defined in terms of h. And so that should be very similar to what you've seen before, provided that those limits exist. Now, you've used the definition of a limit before, so we're not going to do that now. We are just going to jump in and do some examples. So example 1, find the first partial derivatives, fx and fy, for that given function. So here's the idea. If I'm finding fx of xy, I'm going to hold y constant, or I'm going to treat it like a constant. So on my fx of xy, that first function, or that first term, just becomes a 3. So then this middle term, I keep y squared constant. Y squared's just a number. So the derivative of x squared is going to be 2x, and then I have that y squared. And then that last term, again, y is just a number, so we ignore it. So we're going to end up with 6x squared, and then we have the y. So then if I want the first partial with respect to y, this time I'm going to hold x constant. I'm going to hold x constant. So this first term, 3x, that's just a number. When I take the derivative of that, I'm going to get 0. So then that second term will become negative 2x squared y. And that last term, if I keep x squared constant, I just treat it like a number, I'm going to end up with 2x cubed. So those are my two first partial derivatives. And that's the idea in this box here. For f of x, we're going to treat y like a constant. For f of y, we're going to treat x like a constant. Okay, we need to know or talk about some different notations. So like you might see like this, that's the first partial with respect to f. It's also written like this. And that symbol means partial. So you've seen before df dx, or maybe you've probably seen dy dx. That's not the same. That little delta tells us it's a partial derivative. Or it might be in terms of z, if your function is defined in terms of z. Or like this. So these two are both only apply if z is equal to some function in terms of x and y. And then if you're going to evaluate, so if I want you to evaluate that partial derivative at some value, you might see it written like this. The partial of z, maybe with respect to y, evaluated at the point AB. And that's the same as f of y evaluated at the point AB. Okay, so we're going to do one more example where we find the derivative, and then we're going to talk about what does that actually mean. So if we look at this example 2, again, we are finding f of x and f of y, but this time we are evaluating. Okay, so if we start with the first partial with respect to x, this here is a product. This is x multiplied by e to the x squared y. So we're going to have to do the product rule. So this becomes e to the x squared y plus, okay, treat that y like a constant. So we have 2x times x, which would give us 2x squared y e to the x squared y. And then, if I find the first partial with respect to y, so I'm treating x like a constant, this would become x cubed e to the x squared y. Okay, so now I want to evaluate at the point 1 comma natural log of 2. So that would give me e to the natural log of 2, add 2 natural log of 2, e to the natural log of 2. So the first partial of f with respect to x at 1 comma natural log of 2. This is just 2. So we get 2 add, this is also 2. So 2 add 4 natural log of 2. And then if we want to evaluate the first partial with respect to y at that point, we get 1 times e to the natural log of 2. Which just gives us plain old 2. Okay, so it's important that we can find these partial derivatives and that we can evaluate them, but the next logical question should be, why do I care? What do these numbers actually mean? So let's talk about geometrically what we're finding and what these partial derivatives represent. Okay, so now that we've looked at calculating some partial derivatives, let's talk about what these partial derivatives actually mean. So on the figure, you're going to see that we have that blue figure. Let's say that that is z, which is some function of x and y. And then we have some point P that is on that curve z. So let's say that we first look at that point in the xy plane. So this is our point in the xy plane that we then are going to reflect up onto our surface z. Let's start with this tangent line here, this tangent line T1. What you should notice is that when we slice that through the figure, we end up with this red curve here. So that black line is the slope of the tangent line, and that looks like it is parallel to the x-axis. Parallel to the x-axis, we are then keeping y constant at some value. In this case, that value would be y is equal to b from this point here. So then, if we calculate the partial of f with respect to x, it gives the slope of the tangent line, or the tangent plane really, in the x direction. Okay, so if we think about what does that mean? Well, when we go back to y is equal to some f of x in 2 space, when we found the derivative then, that was how y was changing with respect to x. So this was just before. So now what we're doing is this tells us how f, or z, changes with respect to x when y is constant. So in 3 space, or a function of 2 variables, our partial derivatives will tell us how z is changing with respect to another variable. So let's take a look at this example 3. We are going to find the slopes in the x and y directions at that point for z, then we are going to interpret these values. So if we start by taking the derivative with respect to x, there's only one term that has an x in it, so everything else is going to drop out and we just get negative x. There's only one term that has a y in it, so our partial with respect to y is negative 2y. So now if we evaluate at the point 1/2 comma 1, we're going to get negative 1/2. And if we evaluate again at the point 1/2 comma 1, we're going to get negative 2. Okay, so what I am most interested in, though, is interpreting these values. What do they actually mean? Well, this is how z is changing with respect to x. So that negative 1/2 tells us that z decreases 1 unit for every 2-unit increase in x at this point. Likewise, for that negative 2, that is the change in z over y. So this tells us that z decreases 2 units for every unit increase in y. Again, at this point, 1/2, 1. Okay, so you might be asking where this is going. Well, not in this video, but eventually, later on, we've used derivatives to find max and mins of a function, so we're going to do that. We've used derivatives previously to find tangent lines, the equation of a tangent line. We're going to do that, except this time it's a tangent plane. So that's what you can look forward to further on in this unit. Now, if you have a function of 3 or more variables, it's the same idea. So let's say we have a function w of x, y, and z. We can find the derivative with respect to x, the partial with respect to y, or the partial with respect to z. If we're finding the partial with respect to z, for example, we're just holding x and y constant. Okay, so next thing that we're going to talk about is higher order partial derivatives. So we have some notation we're going to take a look at before we actually get into some examples. But I could take the derivative with respect to x of the derivative with respect to x. So this is saying I have the derivative with respect to x, and I'm going to take the derivative with respect to x again. So I could write that like this, or I could write it like that. Or I might take the derivative with respect to y of the derivative of f with respect to x. And that's written as f of xy. So then again, what this notation means is take the derivative with respect to x first, then y. So let's do some examples just so that we can get our head around this notation. So f of xx. So I'm going to start by taking the derivative with respect to x of this function. So that's going to give me 3y squared, add 10xy squared. Now I'm going to take the derivative with respect to x again, which would give me 10y squared. If I want fyy, I'm going to need the derivative with respect to y first. So that would give me 6xy, subtract 2, add 10x squared y. And now I'm going to take the derivative with respect to y again. So I get 6x, add 10x squared. Okay, so then this one, f of xy. I start with f of x, and then I take the derivative with respect to y. So I already took the derivative with respect to x. Now I'm going to take the derivative with respect to y. So I would get 6y, add 20xy. And then lastly, this f of yx means I take the derivative with respect to y first and then x. So I get 6y, add 20xy. Now, what we should notice is that in this case, we ended up with f of xy is equal to f of yx. Now, the question is, does that always happen? Is that always the case, or was this just a nice coincidence? Well, conveniently, that leads us to our next theorem. If f is a function of x and y, such that both f of xy and f of yx are continuous on an open disk R, Then for every xy in R, f of xy is going to be equal to f of yx. So we're going to look at a similar idea with 3 variables this time, though. So you have this function f, and we want to show that these are similar. So I'm going to start on the left side, f of x, z, z. Well, I'm going to start by finding f of x, which I get to be y e to the x, add natural log of z. Then I'm going to take the derivative of that with respect to z, which is 1 over z. And then I'm going to take the derivative of that again with respect to z, and I get negative 1 over z squared. So then I'm going to find f of z, or this middle one is going to be f of z x z. So starting with derivative with respect to z, I get x over z. Then if I take the derivative with respect to x, I get 1 over z. And then if I take the derivative with respect to z again, I get negative 1 over z squared. And lastly, I'm going to find f of zx. So again, starting with the derivative with respect to z, which we already found, x over z. Then taking the derivative with respect to z again, I get negative x over z squared. Lastly, finding the derivative with respect to x, I get negative 1 over z squared. So all 3 are equal. What does that tell us? That order doesn't matter. Okay, so last thing that we are going to do is a little bit of a review from Calc BC. What do you remember about implicit differentiation? So oftentimes last year in Calc, you might have something like y is equal to x e to the x, and you had to find the derivative. But then do you remember what you did if you had something like x squared plus y squared equals 1, and you were asked to find the derivative? Now, you could solve for y, right? And you could say, okay, my y is plus or minus the square root of 1 minus x squared, and you could take the derivative of that, but it's not convenient. And sometimes you can't solve for y. And so hopefully you remember that when you were given something implicitly, so something not written as a function, you used implicit differentiation. So that's what we're going to review a little bit now. It might be a little bit dusty in your brain, but hopefully as we go through this, it's going to come back. Find the slope of the sphere, x squared plus y squared plus z squared, in the y direction at that point. Okay, so first thing, what is our goal? If we want the slope in the y direction, so slope in the y direction, we are looking for the partial of z with respect to y, also written like that, at the point 2/3, 1/3, 2/3. Okay, so then what we're going to do is we're going to take the equation we have, and we are going to differentiate with respect to y, because that's what we want up here. Okay, so when we do that, here's what that gives us. I have to differentiate with respect to y, x squared. Then I'm going to differentiate with respect to y, y squared. And then I'll differentiate with respect to y, z squared. And I'll differentiate with respect to y, 1. And we can do that because when we're taking the derivative of functions that are being added, we can split up that derivative. Well, we know that x squared in this case is a constant, or x is a constant, so all of this is 0. 1 is a constant, so all of this is 0. The derivative of y squared with respect to y is just 2y. And this is where maybe our brain is a little dusty from last year. Derivative here, derivative of z squared is 2z, but I differentiated with respect to y. So writing this again, this is 2y, add 2z, the partial of z with respect to y. So what that tells us then is the partial of z with respect to y is equal to negative y over z. So if we evaluate at the point 2/3, 1/3, 2/3, we get negative 1/3 over 2/3, which gives us negative 1/2. So again, what does that tell us? What that tells us, when we're on the sphere, we're at this point moving in the y direction, so we're keeping x constant. Z decreases by 1 when y increases by 2, again at that point. So this was a throwback to implicit differentiation. Hopefully you remember that from BC. If not, you might need to do a little bit of review. But this one, just so you know, because it's partials, it's called implicit partial differentiation. And like I said early in the video, this is really useful. We're going to be doing a lot with it. And so in the coming videos and coming notes, you'll see some applications of this. If you have any questions, please make sure you bring them to class. See you soon.